Okay, this is one of many videos in which I show you how we might apply Newton's second law to a few practical examples. So I often do these problems in class, particularly this one here, because it's sort of fun to see students jumping around. But if you missed class, or if you just want to review how we solve this problem, this video is for you. Let's take a look at it. So a person jumping example, how much average force must whatever student is that we have to do this in class for this video. I'm going to just go ahead and make someone up. Let's call him Joe Physics, who has a mass of 80 kilograms. Exert on the ground when jumping to a height of, well, for Joe Physics, let's say he jumps to a height of 0.75 meters, which is about a 30-inch vertical, which is pretty good. And again, in class, hopefully we've had a student jump and we actually measure their jumping force, so how hard they're having to push off of the ground. So for this one here, let's use this fictitious data. So let's go ahead and see just how hard that person would have to jump off that ground or push off that ground in order to reach that height. Now, when we go to solve this, it's important to recognize that there's different kinds of motion going on here. Let's separate out these things here. This is the jumping portion, where they're actually sort of exploding off the ground, sort of from that crouched position up to the point where now they've left the ground and they're just in a state of free fall. So when I'm solving these problems, I really have to be concerned about where the acceleration changes, and I have to sort of separate these two things out. Okay, and so we have different accelerations. During the jump, the acceleration is upward. They're taking their body from rest and getting to some sort of launch or jump velocity. And then once they leave the ground, they're just simply like a ball traveling through the air. They're accelerating at g. Okay, so we have to separate out those two motions. Now, where do we begin? Let's see. Based on this, it looks like we actually have enough information here to sort of determine how fast they left the ground. Right? They went to a height of 0.75 meters or 30-inch vertical. Let's go ahead and start this, number one, by using UAM equations and free fall. And we're going to use that to find the jump velocity, how fast they left the ground. Okay, so let's see how we might do that. Let's see, delta y max is 0.75 meters. That's their jump height. So that's occurring up here. V initial is how fast they left the ground. So that's what we're going to be looking for. V final is their velocity up here. Well, once they've gotten to their maximum height, they've stopped moving. And while they're in the air, they're accelerating at g, which we're going to call downward, is negative. We have enough information there to be able to determine v naught. I'm just going to go ahead and use this one. V final squared is equal to v naught squared plus 2a delta y. And then just plug in these numbers here. V final 0, I'm looking for v initial. So v initial squared is just equal to a negative 2a delta y. And so v naught is just the square root of this. Go ahead and start plugging in these numbers. And when I go through and do that calculation, I get the jump speed of about 3.8, looks like 3.83 meters per second. And I'll probably just round that to 3.8 meters per second and go from there. Okay, so that's part one, their jump velocity, how fast they left the ground. Now for part two, I might determine what their acceleration was during that jump. Okay, so I'm going to allow the jump velocity, which was the value we calculated there, which was our initial velocity for our jumping portion. It is now the final velocity for the actual jump. Right. So once they've left the ground, they were traveling at 3.8 meters per second. Over here, we're going to say they started at rest and they got to that eventual speed. So now we're going to use UAM equations to find A up for that jump. Okay, so what is their rate of acceleration? Now, to do this, and oftentimes in class, I ask students, well, what do you need to know in order to calculate the value for A? For this video, I'm just going to tell you that this person is sort of crouched down about 0.2 meters. Okay, so that's sort of like the crouching phase where they sort of bend their legs and then explode upward. They push through a distance of about 0.20 meters. Then again, that's variable. It depends on the student in question. But for this video, let's go ahead and assume that. So delta y now is 0.20 meters. That's their distance that they're jumping through. V initial is 0 because they start from rest, and V final is what we calculated up here. And we, of course, need to calculate A. We're going to use the same equation that we did there. Very useful equation. It doesn't involve any time values, just distances. And oftentimes distance is an easy thing to calculate or measure in our real life. I'm looking for A's there. Since V initial is 0, it just becomes V final squared all over 2 delta y. And we plug these numbers in. And for that, we get about 37 meters per second squared. So it's a pretty good jump. That's almost 4 G's worth of acceleration. And there we go. That's part 2. Now part 3, the actual question that we're trying to solve is just how hard they're pushing on that ground in order for them to be able to generate that speed off the ground so they can get to that height. It's important to draw an FBD here. Now when they're just standing there, or maybe they're crouched but they're not moving, the normal force would be equal to their weight. Okay, they're in a state of equilibrium. But as they're exploding upward, that normal force must grow quite a bit to be able to produce that kind of acceleration. So let's go ahead and redraw that FBD for the jump to show a much larger normal force, F sub n. And that's because the acceleration here now is pretty big, 37 meters per second squared. Right, so we have to have a pretty big unbalanced force to be able to do that. Of course, how we're going to find that unbalanced force is by using Newton's second law. Sum of the forces on geophysics is equal to the mass of geophysics times the acceleration of geophysics during that jump. And so let's see, we have 2 forces there, the normal force minus the weight force, and that's equal to the mass. I'm going to drop all those GPs there. You understand it's all for this particular person. And F sub n is just ma plus, the weight is mg, so let's just go ahead and write that. And we see it's just the mass times a plus g. And let's go ahead and plug those in. That normal force is equal to 80 kilograms times 37 plus 9.8. And when we go through and do that calculation, we get about 3,700 newtons of normal force, which is quite a bit bigger than normal. Over here, the weight force and the normal force are only about 780 newtons. So when they're jumping, that normal force becomes really large, and that's simply because they have to be able to generate a lot of upward force to get to that jump velocity. So there we go, about 3,700 newtons of force that they're exerting on the ground. Of course, the ground is what's pushing them up so they can get up to that particular height. There we go. That problem solved for you.